The last model we're going to look at is RT, Relational Transformers. This is a foundation model that is described, defined, designed to begin with for relational databases. Okay. In the description, it doesn't go through graphs or heterogeneous graphs, which was quite unique when the paper was published in the sense that this is a deep learning model over relational databases, not going through graphs, at least not directly. Indirectly, there is an underlying graph there, but you will see that it is designed from the beginning for the relational context. Okay, the knowing that it is a collection of connected tables. Now, it is designed for in-context learning, and we'll see what it means. Okay, of course, you can also use it for fine-tuning, and we'll also see that in some sense it can serve as a zero shot in certain types of tasks. Okay, we'll discuss that. A lot of the ideas are similar to Griffin. There's one major technical difference, how they use the attention. So remember that Griffin builds a representation of facts, and the representation of a fact attends to the cells. Okay, facts attend to cells and meta data of the cells. Okay, RT uses self-attention. The focus is on representation of cells, not facts. Okay, and each cell attends to a set of cells. Okay, and these can be different set of cells, and they stack layers on top of each other. We'll see that next. Okay, this is an illustration or a description, a visual description of the system from the paper. This is the RT architecture, and we'll understand each component at a time until in the end we'll get the full picture of this one. Okay, now we're going to use this notation of references. So remember that a fact F references other facts according to the foreign keys. Okay, for example, this fact F here references this fact by the 25 and this fact by 89. So there's only a limited number of facts that F can reference to, and we denote this set of facts as ref D of F. We're going to use that again and again, so remember this notation. Now, RT as a foundation model for relational databases applies to all schemas. Okay, it doesn't care which schema you give it. But it does make one important central key assumption that the schema involves a task table. This is where you define your task. There is the key, okay, of the entity for which you want to apply your prediction, classification, or regression. There is the value that you want to predict, and there is the time of the validity of the statement. Okay, when the example was the example or the task is valid. Okay, this is important because this task table is used to store the in-context examples. Okay, so it is quite central in the design, and it means that basically if you have a new data set, okay, a new database, then you need to designate table or build and designate a table as a task table with this specific signature. Okay. Also, when they process an example or a tuple, they make sure to use only information from the past, previous, older than the task role, the specific task, and not rely on future information. That's a standard. Okay. Now, the first thing is that for every fact F that we want to predict, we build a random subset of the database. We do not use all of the database for that, but we build a context, okay, df, around the target fact F, and we are going to process this one. And this is done by applying randomized BFS as follows. We start with the fact F, that is our task. We add several other target facts with known values. Okay, this is for in context learning. Okay, and then we apply random BFS. We take a fact from the database or from the set df, and when the fact is visited, first we add all of the facts, the few facts that are referenced by this fact that we took out, and we also add a random subset of facts that reference the fact that we visited. Okay, G, if we visit G, then we reference or we add G primes such that G belongs to the ref of G prime. Okay, and we do that for a random subset of the facts until we reach some size that is predetermined, like 500 or 1024. Okay, and again, when we construct this set, we make sure not to include facts that are newer than the task fact that we are referencing or applying reference for. Okay, so this is how it looks like. So we have here several tables. Okay, this is from the commercial domain. And so we have the task and the original database relations. Here it's a user item and sale. Okay, now they make sure to identify here for later use the table names. These are going to be used. The column names, okay, the task rows in context labels. And this is the target row. This is a must cell. These are going to be the tasks on which you are going to do the pre-training. Okay. Here they give an actual example from the H&M dataset where they say, okay, so we have here, we want to predict the sales of an item at a specific time. So item sales row, that's the task. So this is what we want to predict. This is the target row. It applies to some article, to some item. And then this item is also associated with many other task rows that are known, okay, that are known by the time of the prediction because they apply to the past, they apply to older timestamps. And what else do we have in this context? So this article is connected to the transactions. Each transaction is connected to customers also, okay? And again, each customer is associated with several transactions of other articles that they've made, and each transaction is associated with its article and so on. So that's basically the context that we have, a real context that we have for a specific target element. Okay. Now, I remind you that we use this notation of D cells, data cells, to denote the cells of columns that are considered data columns, not used for keys or foreign keys. Okay. RT looks at several data types: numeric, Boolean, timestamp, and text. Okay. We start with a basic representation, okay, the feature representation of a cell C. What is it? Very simple. First, we have a representation per type of the value of the cell. Okay, Z T of A. So this is our cell. It belongs to the relation R and the tuple T, and the attribute is A. So we take the value and we have an embedding of that, an initial representation of that value according to the type. Okay, so this is the original representation. We multiply it with a weight matrix that applies to the type. Every primitive type, numeric, Boolean, and so on, has its own weight matrix. So that's the first component of the representation, the value, a representation of the value. In addition, we have a component that applies to the metadata. E of AR, A is the attribute, R is the relation name, is simply a text encoding of the text, A of R, price of items, address of a customer, of a user. Okay, so this is the encoding of that. So we use some text encoding, some language model that encodes this text. That's this component. So in the end, we have some linear combination of the value representation and the representation, the textual description, the textual representation of the metadata of the cell. Okay, that's the cell encoding. Okay, a special case is when we mask a value. Okay, if we mask a value, then we cannot know this part, ZT of A. So instead of this whole component, W tau ZT of A, we use a mask vector M tau. Okay, of the needed dimension, and this is the same mask vector for all the predicted values of this type tau. Okay, so here's an example. So we have here one of the databases, or one of the tables of the database, and here are two cells. This cell will have the encoding, the weight matrix of 10, because this is a type of a year, plus the representation of the number here, 2025, plus some component over the encoding of year of Tuk. This is the Tuk relation. Same for 93, but now we'll use the num weight matrix. And this one is grade of Tuk. This one is our task table or the task row. So we encode it in the same way, but with this M1 to MD. Here I wrote the value of target, which is, like generic to the target. But in a real application or in the implementation of a RT, it doesn't need to be a generic name, not value of target. This can be sales of items, sales of user. Okay, so purchases of a user. So it can have an actual meaning. Okay. So basically it looks like that. We start with the context window. It has a set of cells, okay? And we collect the cells from this context window, and each has its representation. Okay, it's column of table, that's the metadata, plus pair, type, encoder, which is one of these values. Okay, so that is this part. Now, given our context window, our sampled context window, RT actually looks at three specialized contexts. And here we're using the structure of the database. There is the column context. All the cells in the column of the cell. Okay, so how do I write it here? If our cell is RTA, then I write it like RT prime A, some other T prime in R. Okay. Similarly, we have the feature context. The feature context is basically the other data cells in the tuple of C. Okay, so this is same R, same T, but possibly a different A prime, plus the data cells, data values, or the data cells, sorry, of the rows, the facts that are referenced by T, by the tuple of the cell. Okay, so if the cell belongs to a tuple, the tuple references some other tuples. We also take their features as well, their data cells as well. So this is still a small number of features. And then there is the neighboring context. And this is the set of cells or data cells that belong to tuples that reference the tuple of C. Okay, our T belongs to ref of this fact, some R prime T prime. Okay, some R prime T prime that references T. So three types of context: the column context, the feature context, and the neighboring context. And then the model basically combines, sums up the different attentions. We'll see what the update does, but it starts with your original basic representation and then applies an attention to the column, adds an attention to the feature set, attention among the neighbor context, then full attention, all of the facts in DF, all of the cells in DF, and then some final adjustment layer of an MLP of what we got. Okay, and every time we add the previous result to the update. So in the end, we sum up all of these parts and include the skip connection and so on. Okay. Now, this is one layer, and the transformer architecture stacks multiple of these in the experiments. Okay, so this is a special form of the transformer because it's not one type of attention. Okay, you have four types of self-attentions. Now, for each context set, SC, neighbors, features, column, and so on, we apply this update function. What does it do? Well, quite a simple case of attention. So we are combining several heads, okay? And each attention head, well, what does it do? So the question is, what is the query? What is the key? What is the value? The query is the representation of C, the previous representation of C, XC, times some weight matrix for the query. The queries are, well, the same values from the previous layer times a key matrix, and same for a values representation times a value matrix. Okay, and this is our attention, pretty standard attention. Again, to each set, we apply this attention layer and then combine them. Okay, and basically that's it. So you can see here in the example that after we have our cells and we apply the basic encoding, we apply this layer, 12 layers in the experiments of the attention, where we start with the column attention, then add up the feature attention, then the neighboring. If this is our node, then these are the neighboring attentions. Okay, and then the full attention to all of the cells in the context. Okay, and finally an MLP. Okay, now just as a practical way of delivering this learning and evaluation of the attention, in the end we do something standard, which is that we always use the same multiplication. We attend to all of the nodes in the context, or all of the cells in the context, but filter them using a masking matrix. Where a masking matrix means that if we care about this element, then this is 1, and otherwise this is a 0. And what does it mean? That when we apply our attention, then we also have an element-wise multiplication by this MS telling us whether we need the value, that's 1, or we want to avoid it, eliminate it. So that's a 0, multiplication by 0. That's a technical solution. Okay. Now, that's the model basically. How do we apply it to a new task? Okay, we have 3 modes of operation. We can think of it as just an ordinary model. Okay, that's our model. It's based on transformers. And we can use it as an ordinary, not a foundation model. Take your database over the one schema that you have, train your database on that schema, and apply the usual thing. Forward, backward, they use the Adam optimizer, and that's on the context window. And in the test, you apply the same thing. You sample a context and you apply your model forward in the context. Okay. I can also use it for fine-tuning. Basically, pre-train the model. That gives you the initial weights, and you continue your training on your specific database, on the specific database of interest. Okay, so you can take one pre-trained model and just continue its training on your data set without even knowing what it was trained on to begin with. And there's also the possibility of using it in context, which means that you basically don't use any training, no fine tuning. You don't touch the weights. You simply apply it without any training. And then you ask yourself, okay, but where is the context? We said that. That's the other rows of the task table. Now, in many cases, you do not really need to hand label a few examples or in-context examples for the task. Why so? Because in many cases, what you want to do is to predict the future, but you have your past behavior in the database. You know what a customer did in the past, and you want to predict what the customer is going to do in the future. Okay, so in a sense, you get that for free. And in that sense, the authors refer to this task as a zero shot, actually, not even in context learning. Okay, so that's the idea. Some details about the experiments. They tested on Railbench, leave one out, meaning every time you pre-train on all of the data sets but one and test on the remaining one. These are the details of the dimensions, 8 attention layers or attention heads per layer, sorry. And something special is that they use for the activation this sigmoid linear unit, which is sigmoid times x. Okay, which works well for them. Text encoding they did through a sentence bird. Okay, so this is also a conventional approach. Okay, so here are some experiments from the paper, and what do we see? Well, the cut lines, the dotted lines, or the dashed lines, are basically non-foundation models. So one of them is RT, untrained, just used as a model. The other one is Griffin, untrained, the green one. And this is a GNN, basically, a heterogeneous GNN, the orange one. So you can see that, without examples, they have bad, basically random performance. This is a ROC AUC, very close to 50%. The pre-trained Griffin and RT, okay, using the in context, the context that they were provided, start with a good performance, okay, close to 70%, which is non-trivial. And as they increase the number of steps of fine-tuning, they eventually all match. Okay, so the advantage is really here in this area where you don't need too many examples for, or you don't need to retrain the model. You just use it in context. Okay. This is a similar experiment now with a regression. So they don't use area under the curve, but R2. Okay. And again, you see a similar behavior. Okay. So that was it about relational transformers. And I'm going to end this module with some key takeaways. Okay, so we talked about foundation models for tabular and relational data. They generalize across schemas. That's something that is important in the case of the focus of this course. The fact that we are using schemas to represent the structure of our data allows us to define the foundation models in that sense, in that terminology. Foundation models generalize across schemas. Okay. We saw several approaches, okay, for foundation models. Basically, each one used transformers in one way or another. TabPFN used the synthetic data sets. TabLLM used an LLM plus the fine-tuning of extra parameters. So we saw this idea of parameter efficient fine-tuning. Okay. Griffin uses row to cell or fact to cell cross attention and combined it with a GNN in a graph approach. RT used cell-to-cell attention, stacking several layers, each attending to a different collection of cells in the context. Okay, so we saw different ways of using transformers and incorporating the structure of our structured data. I'll repeat the statement that this field is moving very fast. We're looking at very new models, and as we speak, new and newer versions or models are being created. So specific systems will not last long. That's for sure. But the underlying ideas that we've seen in this module, they will live longer. And that's the final message. Thank you very much.